Okay, let's start. So I wanted to um, present one particular method today on uh, processing sensor data using machine learning methods, and one which is fairly easy to realize also. There are a whole bunch of techniques out there. Some of them are not easy to implement on Hexaware, either because the code is not readily available or you are memory constrained. But the one method that I wanted to go over is, and then also there is kind of the big kind of popular approach now, which is the whole deep learning, which maybe we'll come to next week. Um, uh, so I mentioned last time that when so essence of machine learning is that instead of writing a program where you kind of you create an algorithm based upon your knowledge of physics of the phenomenon, heuristics, thumb rules, whatnot, which so is the initial inclination. The idea out here is that we want to create a model which is learned from the data. And there are several advantages of it. So just to give an example, yesterday one of the student team came and spoke with me, and the problem they were facing was that uh, so this thing involved kind of movement of hands and stuff like that, and there are kind of as they were tracking the speed and all, there are some unusual characteristics in the output that come, and that very much has to do with the particular person who was kind of trying it out. So to fix that, they're kind of manipulating, adding some additional restrictions and all. The problem with these kind of approaches is not very robust in the sense that it might work for that particular person, but what if we want to try it on someone else? There's no systematic way of kind of approaching that. So what the more systematic data-driven approaches kind of do is, instead of patching your heuristic with what you've seen, they kind of approach the problem that, is there a model that we can learn which performs well across a broad range of scenarios. And there are many ways you can go around learning this model. The one which is, as I mentioned last time, is dominantly used is something called supervised learning, which I'll go in more detail. But it basically is akin to saying the following, that let's say you have a teacher, and a teacher gives you lots of examples of questions and the corresponding answers. And from that, you learn how to answer questions. Unsupervised learning is, I will just give you questions, and you are going to figure out that the questions have some pattern. And then there are kind of all these other things. Active learning refers to the fact that when I make some observation, then based upon that observation, I ask a new question. Okay, so I kind of probe the world based upon what I have learned. So that's active learning. There's reinforcement learning, which, as I mentioned, is something which has been in news quite a bit because it's been used for all these game playing systems. And kind of the idea in reinforcement learning is that there is feedback from the environment, feedback from the outside. So to give you an example, Google's AlphaGo, which is the program which beat the world champion in South Korea, the way these things work is the machine plays against, well, a copy of itself really, and multiple such games are done, and they basically try out different strategies, faced with a particular state of the board, what move should be made, and across many games they basically kind of learn that, oh, given this state, this is the right action. So they're learning a policy in a game playing situation. So that's reinforcement learning. Transfer learning refers to, let's say I know how to do very well one thing. Let's say I know very well how to play piano. And what if now I have to play flute? Do I start from scratch? Well, not really, because there is a underlying basis which is very similar about the music theory and how the notes work and all. So hopefully I can take much of my piano playing model and then throw away some part of it and add some to it, right? And that's how we do a lot of tasks in real world also, which is if I already know how to do something, then so let's say if I already, another example, let's say I know how to identify animals in natural scenes, and now I give you a task of identifying flowers. Well, presumably to be able to classify animals, you probably had to learn things like how to detect edges, shapes, circles, straight lines, those kind of things. And those are probably going to be useful for flowers also. So again, part of your model, which corresponds to those simpler features, could be carried over. So that is transfer learning, and it's again kind of a very an area which is very much an active research topic. Federated learning means how a collection of things can learn together. So a bunch of agents, bunch of let's take activity learning by individuals. Okay, so different individuals wearing these sensor devices going around, they're all collecting data. Instead of each one learning on their own from their own experiences and what they're observing, what if we were to all share things? So we form a federation and we learn a collective model together. So these are all examples, but we'll stick with kind of the more routine ones, and which is supervised learning and unsupervised learning. And within supervised learning in particular, there are two different kind of tasks which get done. One is classification and the other is regression. Regression means that I have to estimate some numeric value. So you can think of it as my output lies on some sort of a number line. So there is there's some sort of a relationship between values, that is, one follows the other. There's a distance between things. 5 is closer to 4 than it's to 3, so there is some sort of an ordering, some sort of a distance that exists. On the other hand, classification is more about categories. So is this an apple or an orange or a pear? Okay, there is no notion of one being closer or farther than the other. They are just distinct points in the space. And there are many schemes that exist within these. The one which I'm going to spend some time describing today is called naive Bayes, because it's used, well, it's called naive because it's super simple, and Bayes because it's based upon Bayesian methods, and it's actually pretty easy to implement. And you'll see how at least one particular method kind of works. There are others which are also simple, and then of course at the very bottom out there is neural networks. So the process of supervised learning, as I mentioned last time, starts around first collecting some raw sensor data, which is labeled. That is, somehow you collected the data and simultaneously you also collected the labels. Now, of course, collecting labels itself can be a pretty onerous task. In some cases, you can rely on things like Amazon Mechanical Turk, which I mentioned last time, which is this crowd of people out there. So for things like images, that could be an option. You have a bunch of images, you want to get them labeled, you just farm them out to people, and maybe every image you will get multiple people to label and then kind of do some sort of a voting on them. So you get a reasonably robust label out there. Some other cases, you could rely on cameras, you could rely on self-reports. So like, for example, one technique that we often do is with humans with medical type sensing and all, we periodically give them a questionnaire. What were you doing recently, or stuff like that. Now that can be very burdensome, so you can't have continuous labeling in that case, but it still gets you some sort of a data. So let's say somehow we have solved the labeling problem. This is not a very sexy problem in the sense that, hey, labeling sounds very boring, but it's actually a pretty hard problem, and sort of a good topic for research, which some people are doing, but most people chase kind of the more obvious problems. But I think there's pretty cool possibilities out there. Then you take this data, and during the offline phase, which is kind of the training part, so this is offline, we extract features, and that presumes that somehow you have figured out what the features are. And it's kind of an iterative process, because going in, you don't know what features are, so the set of features itself is kind of like a parameter of your overall approach. Your good strategy is to come up with a set of features that are inspired by similar tasks, And that's why I had shown that list to you last time, but it was a very long list, and you're going to intuitively, let's say, if you are trying to do something about, I had that example yesterday, like am I wearing hexagon on left hand or right hand? I might say that, energy will matter, because if I'm using my well, that's a bad example. Am I on the dominant hand or not? Okay, so the energy will matter a lot. Okay, or in other cases you could say maybe it's the frequency that matters. So there's some intuitive guidance that you can bring to bear. So you can say the choice is important, and choice may be guided by intuition, physics, whatnot, your understanding of the problem. And this is where obviously bias can come into your bias and competence as a designer of the system would come into play. But let's say we have this set of features. So now what we have is we have a set of samples, and for each sample I have a corresponding feature vector. In our case, it could be of an activity thing. Maybe I have a whole bunch of examples of activities of different type, walking, running, and all. And for each one of those, I will have the corresponding feature vector. Then I'm going to train the model, and training the model basically means that I have some mathematical structure in mind which has some parameters, and I have to find a value of parameters for that model, so that if I were to feed my my feature vectors to it, then the label that will come out of that mathematical function will match the label that I obtained as part of my training set. So find the so my goal out here is find parameter theta such that f, which is my mathematical function, f at theta for x is close to y, where y is the label. Okay, so that's the goal, and my job is to estimate theta. And in general, depending upon what f is, that would be. Now, a very common strategy in these things is kind of a greedy approach. So you will start with some value of theta, and then you would say, if I were to perturb the parameter a little bit, am I getting closer to the answer? Okay, so kind of I find what I am predicting on the set of vectors I have, the y's that I'm predicting, and I want to find how far away they are from the truth, and I kind of compute the derivative and then kind of move in the direction of the gradient. So basically it's kind of like I'm trying to move towards the valley, which is my optimal point, so I kind of go downhill. So it's called gradient descent. We follow the gradient, and there are a lot of variations on it, but that's kind of the intuitive idea. That's one of the ways you can do it, because almost always finding f any other way is very hard, because the f is highly nonlinear. Okay, so for linear systems and convex functions, there are good theories out there, but we are dealing with f tends to be extremely nonlinear. There are lots of valleys and peaks, and if I were to think of that error function. So somehow through some sort of an iterative process out here, I find the parameter theta. You see out here that the iteration is not simply to training the model, but it's actually also to feature extraction. Because if things don't work out, then you'll say, aha, maybe my choice of features is not good, and I'm going to go back and revisit the features. Maybe window size is wrong. All of these things are in the play. And then, of course, the training strategy itself. Maybe some variants of the derivative. There are a whole bunch of kind of optimization methods that sort of exist that one can bring to play. At the end of all of that pain, you have now a model with the parameters that you believe are good parameters. And there is also some additional things one has to worry about out there. If your model is extremely rich in parameters, then there is a danger that you can overfit. So if I give you n points, and if my model has n parameters or n parameters, then I can always fit a curve through that, right? I mean, or usually, like, if I give a bunch of points, then you can always fit a n degree polynomial through it. So that's a bad idea, because that means I'm overfitting, and then anytime you give me something which is a teeny bit different, I will have a wildly different error. So during this model process, we kind of try to strike a balance that do well on training data, but we also want to do well on things that we haven't seen, kind of this ability to generalize. So the way it is done is, and this is very good practice, when you get the data, you divide it into three parts. So you have a bunch of labeled data, you divide it into three sets: training, validation, and test. And this test you keep away. You are not going to look at it at all, okay, until the very end. And then training and validation, what you do is you train the model and then see how the model does on the validation. And then you repeat that process until you get something which is doing well at the validation. And so that is your way of saying that, okay, I have some ability to generalize. How you select training versus validation is also important. So let's say you are seeking to generalize, let's say you are trying to do activity recognition. So, and you collected data from, let's say, 100 users, and for, let's say, 10 days each. So one way you can say is, I have 1,000 person days of data. I'm going to put very common number, 80% to training, 20% to validation, and my testing is separate, okay? The problem with this is that the system is getting to see every person's data. Perhaps a better approach would be my validation set should consist of users that are not there in the training set at all, so that I also make sure that I generalize from person to person. So very important to have data which has sufficient richness in type of activities, type of people, stuff like that. And then once you have a model which you believe is a good model, is performing well at validation, then you are going to run it on test and report the results. You should never iterate on the test. The problem is that if you iterate on the test, then it's kind of like knowing the exam, and then you are getting to iterate on it. So that is recipe for disaster, because you will bring to bear, the moment you iterate after having looked at the, even if your algorithm doesn't, you will bring in a bias, and therefore you will end up with a solution which will not do well on the next test. So test is kind of the real thing, how it does. So all these considerations are important in training. At the end, you have your predictor, and if you did the job right, followed all those advices like how to do validation, how to do testing, hopefully it will do well. And then now, based on the new data, you're going to extract the features, the very same features you finally decided to use, feed them to the predictor, and then outcome will be the label. So that's the basic strategy. How do we all these systems kind of the different supervised learning system kind of operate on this basic paradigm. In fact, toolkits like Scikit and MATLAB and all basically provide you functions corresponding to different parts of this framework. They have a whole bunch of features out there. They have optimization algorithms. Typically, you don't have to do all this loop. You just say, I want to use this optimizer, and it kind of takes care of it. Lots of support in programming languages for feature extraction, signal processing functions, things like that. How to run through batches of data. So all that ecosystem is taken care for you. And of course, they provide a whole bunch of models also. So you can have your pick of models in there. The challenge which comes is the following, that when we face with embedded system is, we are not in the world of Python. If we could run Python and Scikit or MATLAB on Hexaware, that would be great, although very power hungry. We want eventually code which is some C, C++, some code like that, which we have to embed and should be memory efficient and stuff like that. And that's where kind of things hit a bottleneck, which is currently tools are not very good at spitting out implementations from your Scikit or MATLAB and all. Ideally, MATLAB has something. If you pay loads of money to MathWorks, they actually will happily sell you a package which takes your MATLAB model and spits out C code. And that C code you can link into Hexaware and work with it, but the problem is that's not part of your student edition. There are some commercial services, like there's one called bigml.com, big machine learning, so bigml.com, and their system lets you export the classifier, the model that you have learned, as a piece of code in a few different languages. Okay, so I've often used their system. They have a free mode where you can kind of learn things on a small scale. And so they'll spit out Python code and all, and then with some effort you can kind of convert it. But otherwise, in typical systems, yes, there is a model, they give you a model object, but you don't really have any code. So if you want an implementation of something, you're kind of stuck there. So then your solution becomes look for existing implementations or writing from scratch. And existing implementations on embedded platforms are pretty rare. This is a field in its infancy in that regards. Because most people currently in academia, they were kind of just take the data and they report how things are doing by running things at backend. So relatively little work in actually some sort of a machine learning library for Hexaware and embed and these kind of devices. Some has begun to change, like Apple provides something for Apple Watch and all, but kind of still in its infancy. So what is necessary then is to limit yourself to things which you can implement easily. Okay. Now, ironically, one which you can implement relatively easily are neural networks, because they're structurally very simple. I'll go deeper into it later on, but I'm fairly sure at least all of you have heard about it, if not have some sense of what they look like. But the basic concept behind all neural networks is that I have neurons. We'll talk very shortly about what they look like. And these neurons are organized into layers, as you see. All the input feeds into the first layer. So this is the input layer. And so input comes here. So my input could be, let's say, an image. And the pixels of it, I can think of them as a big vector, and I feed them 1 pixel per neuron. Or my input may be accelerometer data, and I'm now looking at 1 window worth of data, and I have extracted features from it, and the features are the input to the different neurons. So one neuron takes max value, another takes min value, another takes energy, and so on and so forth. Or maybe I just take the samples and feed them into it. Okay, there are many different ways you can kind of think about this process. And then things sort of in its most general case that happens is that in each layer, the neuron gets the value which is the weighted sum of all the neurons in the preceding layer. So, and then, so those weights are the parameters. So the job of model learning then becomes learning the weights of each one of these, on each one of these edge. And then usually there is also kind of like a bias term out here, a constant term, so for each neuron, a bias term, and that also you need to learn. So the model parameters in this case are the weights plus biases. And then eventually, the output of the final neuron, you can think of them as some sort of a score. So if it's a category, then the highest score is the one which I'm predicting. So I may say, I will consider the output of the first neuron to say this is walking. Output of the second neuron corresponds to sitting, and so on and so forth. And my goal is that if it is genuinely a walking activity, then the first neuron should have the highest score. And then there are ways in which you convert these scores into probabilities and kind of think of them that way. Those are details for later, don't matter, but fundamentally I'm trying to say the activity taking place is the one for which the neuron has the highest score. Okay. And then during training, I have to, I will feed the sample input. I will get the score that the network with its current weights is saying, and then I'm going to compare against the desired one. So the desired one basically would have a high score and then no score for the others. So I have kind of two vectors and I look at the distance between them and then try to optimize for it. So all neural networks of which are used for these kind of classification things on a window of data kind of look like this. One optimization which is often done is that instead of having a fully connected network, we use a sparser network. So we make use of the fact that there might be some structure in the things that I am feeding in some cases. So if it is an image, the idea is that I want, and there is nothing special about any particular region of the image. So what we do is the way kind of our eyes operate a little bit, which is each neuron is affected by the pixels in a neighborhood, and then each neuron is otherwise identical. That is, each neuron has same weight, and it is active only. So the idea this way is that whether the object is in one part of the image or another part of the image, there is some neuron which is going to act very similarly. So that makes the layers sparse and reduces the model parameters. But that's kind of the basic idea behind all neural networks. Now, the nice thing out here is it's super easy to implement. If you don't care about, I mean, unless you are doing it on a GPU or some funky hardware, if you're just writing it for a standard processor, it's pretty easy to write, bunch of iterate for loops and all, and you're done. And there are good libraries to kind of do it. The problem is models are huge. I mean, if you just look at this one, I'm producing 4 outputs, and output which is 4 valued, and I'm taking an input which is whatever, which has 8 things. So it's not a terribly huge space that I'm talking about, and yet the number of model parameters there are huge. So these are memory intense, and also because it has lots of parameters. So the other challenge is to learn lots of parameters, I need lots of training data. Okay, and unfortunately, again, particularly in a setting like a course project where you have only a small number of weeks to pull this off, you will not have huge amount of data. So the challenge here is too many parameters plus too few data, or not much data. Okay, not much data. Okay, the problem, if you don't have that much data, then with all these parameters, your model will just learn how to do perfectly because it has very few things to do. So deep learning is not a good strategy for the kind of work that we are doing, unless, and that's one exception, unless you happen to find a pre-trained model. So for things like images and text and speech, there are good pre-trained models out there, and one can adapt them and run them on an embedded platform. But if you are training a model from scratch, you will never have sufficient data in a limited course project type setting to do this thing effectively. So this is not a viable option for those reasons. Just a little bit on what those neurons look like. So I mentioned they are a weighted sum. Well, a little bit more. If they were just a weighted sum, if everything was just a weighted sum, then the whole network is just a weighted sum, right? I mean, weighted sum of weighted sums just becomes a linear thing. So that would not be tremendously useful. We want to express nonlinear things. So what happens is each neuron also has a nonlinearity present out here. So in general, the neuron therefore looks like the weighted sum, which is this theta tx, and then some nonlinearity g thrown on top of it. And it is this summation of nonlinearities and repeated nonlinearities which give neural networks the power that there is sufficient richness in this model so that it can express a large variety of functions. In fact, it can express anything that is computable. Okay, so it's Turing complete. It can express anything, any function that is in principle computable, it can express that. So this G, this nonlinearity, has to be something which has to be well behaved, and a lot of work has gone on in identifying what types of G's are well behaved. And there are some bio inspirations that the way our brain works, but there are also much more engineering perspective. One constraint on G is that G should be differentiable so that we can do that gradient descent game, right? Because gradient descent depends upon finding the slope. So if I cannot find the slope, that is, if you cannot take derivative of g, then I have a trouble. So you want g to be well behaved in many regards. So many different activation functions are there, and these are a few examples. Well, firstly, the first one is not an example; it's linear, so it doesn't do anything. Sigmoid, which basically says I will saturate the output of the neuron so that too high a value is 1, too low a value is 0, and in between there is a region of linearity. Um, uh, this has issues. The tanh, hyperbolic tangent, is another one which is used quite a bit. But the one which is most popular and which I have not shown out here is called ReLU. And it looks like this. For negative value, it's 0 up to some point delta, and then it is linear. And typically delta is 0. Okay, so it's kind of like max of delta comma x is what it becomes. It's called ReLU, rectified linear. So it's rectifying. So rectifier is the circuit which makes everything positive, right? I mean, it chops off in one direction and then it's linear otherwise. So this is what gets used, and there are some suggestions that our brain also has something akin to that, but whatever, it works well in practice and it's very easy to implement. So there are kind of two issues about the type of function that you want. Differentiable should work well, but also should be cheap to compute. Things like tanh and sigmoid are kind of hard to compute there, whereas this thing is super easy to compute rapidly in hardware and software. So activation functions kind of end up playing that role. If my job was not classification but regression, then I will use the value as the one which I'm predicting. Okay, so I will then have a single neuron and I will use its value as the value my estimate, and I'm going to compare it against. In that case, I will not have a label, I will have an actual value. I'm going to compare the two, do some error function, and then play the gradient descent game again. So conceptually, neural networks are great. They have been around for a long while, but they were not used a lot until fairly recently. And the thing that changed is compute power, GPUs, and lots of data. But we have good compute power, but we don't have lots of data. So usually that becomes a bottleneck for a lot of work that we do. On the other hand, if your project or task involves something to do with images or something to do with text or sound signals, there are good models from Google, Facebook, and lots of researchers which can be your starting point. But for a lot of other stuff, that's not what you have. But having said that, some of you are doing things like gesture recognition and stuff like that. You might find something out there, and feel free to adopt it. A lot of people release these models out there, and so if you find something which kind of works for you, acknowledge and use that as a starting point. Refine from that. So now, that's one next step. Now, of course, what did people do before that? So the most a very powerful technique, because it works beautifully and very simply, is called naive Bayes. So what is Bayes' rule? So let's imagine that my input to my system, the feature vector is x, and the prediction of my system y is a label. The label can take a set of values, and x is a feature vector of certain dimension, and each dimension can take some set of values. So overall, maybe the feature vector can take one of, let's say, some set of values. So what Bayes' rule says is that probability that given x I will observe y is equal to probability that given y, that given I observe y, the input was x, times probability of y, this is the prior probability of y, divided by probability of x. Right? So that is everyone familiar with this? I assume you've done some probability course. Okay. So our objective now, the way we formulate the problem is, we want to say I want to find that y that maximizes py of x, and this is called maximum likelihood, because this term Py given x is called likelihood of y. And implied out here is there is some parameters in my model because we'll see what those parameters are. But there are some parameters which we are going to use. So maximizes the likelihood of y. So we want to create a system where this holds true. So now remember I said that x is a vector. You collected together your different features and made a vector of them. Let's say you had d features. So you can think of x as x1, x2 through xd. These are d dimensions of my feature vector. So probability of x given y is really the same as probability of x1, x2, xd given y. And now what we really need to be able to do for doing this maximization is to learn this distribution. Because if I learn this distribution from training data, then I can solve for this problem, right? If I were to give you a distribution for this, and also if I were to give you priors of py and px, I could do it. The problem with this is it has too many dimensions. So you will never have sufficient data to learn this distribution. How do we learn distributions? Let's say I want you to learn the probability distribution of some random variable z. How will you go around doing it? Huh? Sample, right? So I will make multiple measurements of z. I will jot down what frequency they occur at, and that will give me kind of a distribution. Okay, so it would be an estimate, a good statistical estimate. So I have to sample. So I have to have lots of data of x and y, but since x is very high dimensional, I will need lots of samples if I were to think of it this way. So that's not very desirable. You will spend the whole quarter just collecting the data. So what do we do? So naive Bayes, the reason it's called naive is it makes the following assumption. It basically says that the data attributes are conditionally independent given the class labels. So what I'm saying is that if I tell you what the label is, then the attributes are independent of each other. So intuitively, it is saying, let's say, height and time of day are used to predict whatever, when the person sleeps, okay, or how much the person sleeps. Okay. So what this thing is, if I tell you how much the person sleeps, then these two are kind of independent. Okay. What that translates mathematically is that this expression, now since x1 through xd are independent, could be viewed as a product of the condition probability of each attribute with respect to y. So what was basically one very complicated thing now is a bunch of simpler things. And each one of these, because each dimension can take only a small number of values, can be sampled with, we can get away with a lot fewer samples therefore. So what, plugging it back out here, it basically says probability that y equal to k given x, except that x now is this whole vector, can be viewed as the upper term is now the product of xd given y equal to k, probability y equal to k, and then summation. P of x can be viewed as summation over all possible y's, right? I mean, I can always take a probability of x is the same as probability of x given y1 times probability of y equal to 1 plus probability. This term is equal to sigma over all y. So that's what the bottom term is. And what we are looking for is, we are saying the y that we want, okay, is that k which maximizes this expression, right? Because that's our goal, we want to maximize this expression. So, and if you notice, the bottom term is going to be always a constant, independent of what k is, because we are covering over all possible y's. So I can just secure into doing an R max over just the numerator. So that's really what we want to find. So now you see that these, there are two types of distribution that are occurring in this thing, right? There is probability of each dimension of x given y equal to k, and probability of y equal to k. So how many parameters do I have? Well, I have probability distribution of y. So if y can take 10 different values, then I have 10 different numbers, or more precisely 9, because the 10th is dependent. And likewise, if x can take 100 different values, okay, or sorry, xd can take, you can for each d in front of some impact. So there's a bunch of parameters that I have. These are all, they're basically capturing the probability distribution. So now what your training becomes is, given the training data, you have to learn all these probabilities. And that, as mentioned, is an act of frequency counting, right? I have data, I just count among it. So let's see how we can do that. So probability that xi, the ith dimension, has a value vj given y equal to k is number of data samples where xi is vj and y equal to k divided by number of data samples where y equal to k. So I will just do this counting. You have the data, you basically run through it, and you maintain a table, and you, every time you get a data sample, you increment, right? Then at the end of it, you will have the frequencies, and then you go ahead and you calculate this. Probability of y equal to k will be number of data samples with label k divided by the number of data. Now there's some funny terms you are seeing, I'm going to come to it in a moment, but this expression out here is the essence of what we are after. Now there's one tiny little detail which comes up. Try as you might, you will still have certain combinations of y and x which will never be in your training set. So one thing you can say is they don't occur, so the probability must be 0. The problem though is that if these things are 0 and they are entering into the product term out here, then the product term will be 0. So you will almost always end up with an answer of all possibilities would be 0, and that's not very good. Now what you really want to say is it's very small, because that's why you didn't observe it, right? So the trouble creates problem in this scenario if no data for a given value of x. Okay. So what we really want to say is that absence of data means it's some tiny thing. So what you do is, when you are doing this frequency counting game, instead of initializing all the probabilities to 0, you initialize them to a tiny number, maybe like 1. So you say, I'm just going to assume that each one of these combinations occurs 1. And now I'm going to add stuff to it. Or more generally, I would say it's L. So that's what you see out here, L. M is the different number of values x can take. So the denominator will be L times N. And this is like a smoothing operation. So we basically want to avoid saying that absence of observation means the probability is 0. I cannot make that hard statement. So I'm basically going to say that I'm going to start out by assuming everything has a prior low probability, okay, or equal probability, and then kind of work from that. So there are various ways of achieving this effect, but this is what is commonly used, so which is why you are seeing these terms. So these are the smoothing terms, okay. And py of k is given like this. Now again, you don't have to do this during training, because if you are using something like scikit, it does this part for you. You can specify what smoothing to do. It will take care of counting these things. You just have to feed the vectors to it, and it kind of takes care of it. But the nice thing out here is your inferencing is very easy. You are only implementing this equation, right? Given a particular vector, you are going to have to say which k gives me this maximum value, and that's a pretty easy thing to write from scratch. So naive Bayes, the attractive part is that you can implement it from scratch without given the parameter values, and that's why it's worthwhile. And very interestingly, it works well. Uh, you will be surprised that some, despite this assumption of conditional independence, in practice, under a lot of scenarios, it works as well as um, support vector machine and decision trees and all, or at least the gap isn't that much as you might think. There are there is a variant of this which is for continuous variables. So here the feature vectors are all discrete, which is why we are able to write sums and products like this. There is also a variant for continuous things, which is called Gaussian mixture model, which if you had continuous valued feature vectors, then you might want to consider using those. Again, works very well. So your first line of attack can simply be to use one of these simple techniques, because they are so easy to implement, and only when it fails, and it will fail. There are a lot of scenarios like where there is a strong temporal dependence. If you didn't use your window size right and all, you may run into problems. But even there, you can often incorporate features from the previous window, so kind of have a little bit of a history or memory into your system, and you may find that it works pretty well. So naive Bayes and its close cousin GMM, Gaussian mixture model, are kind of good starting points for what to go after. The training is taken care of by the tools. The main attraction out here is that you can write the inference code from scratch without any handholding. Questions on this? So if you just Google for naive Bayes, even the Wikipedia page would be pretty informative. How many of you knew naive Bayes beforehand? Okay, so fair number. So that would be my suggestion, as particularly those of you are doing activity and these kind of things. Just sort of start with this as your first cut. Okay, let's see, how are we doing on time? Okay, I'm almost out of time, so we are going to look at some other methods on Tuesday, but before, so I know like one group was trying to use the support vector machine. Gives good results. The problem is it's going to be a pain to implement on Hexaware. So stay away from things like those. Okay.
In that case, can we like do some like basically processing the Hexaware and then have the tie to the...
Yeah, so that's the other option, which is you run Scikit or something in the cloud and then really think of it as inferences being done out there. Yeah, you could do that. Okay, so in which case you kind of bypass this problem. Not everyone has that luxury, unfortunately. So, and also your features may still be too huge. Okay, so those are some of the decisions you'll have to make, which is some combination of quality of result, ease of coding, and what your application can easily permit or not permit. Okay, so just consider those factors in. But the other thing, like I said, is don't be dismissive of simple techniques. I mean, they work nicely. Yeah.
Why is it that SVM is hard to implement?
The reason it's hard to implement is because SVM comes the standard implementation is something called libsvm, and that is a pretty large code library itself. It's written long ago by some students in Taiwan. In fact, one of those students is a faculty in CS department now. So it's kind of written in an era where they were just writing for, I think the original library was actually in Fortran, and then over time it got, so no one has really done kind of a nice embedded realization of it. So simply taking that libsvm and running it on Hexaware, it will probably not even fit on your on the platform. The other thing is that SVM, depending upon how you're doing, can have lots of parameters, and that can cause issues in terms of RAM. So those kind of things can be done. Don't get me wrong. I mean, I had a student who did libsvm for the signal processors which are there on Snapdragon, which is the chip used in most Android phones. But he had to put in a lot of effort kind of going around doing it and dive into kind of very low level details and all. And again, he never did it with the perspective of making a general release or anything like that. It's just something that he did for his project. So I don't want to say you cannot do it, but it's not something that you can pull off in a course project type setting. Okay. Um, Decision trees are easier to implement. Uh, Linear regression, linear classifiers certainly are easy to implement. And one way you can make linears work is where you include non-linear terms in your feature vector. So like for example, let's say you have some attribute x in your feature vector. You also include x squared and x cubed so that it can stitch them together to create non-linear approximations. So that can work. Neural nets can work if you have plenty of data, or if you keep the neural network simple so that it has few parameters so that the data that you do have is sufficient for it. Avoid the temptation of uh, taking complicated neural nets and then have relatively little data, because you're now trying to learn lots of parameters and you have very little data to kind of work with. So that combination you have to avoid. And I mean, hopefully in your projects you have started collecting the data and all, and how painful it is something you will rapidly realize. It's that initial phase of preparing the data, which is kind of most of the work. Rest is taken care of by these toolkits which are out there. It's that initial part which is the painful thing. Okay, so let's meet on Tuesday. Have a good long weekend.
Do you go to the previous?
Sure.
Okay.
You wanna look at this?